Now, the second example that we're going to look at here involves using a heat lamp to heat something up. So you've basically been told here that you have a heat lamp element with a particular temperature, right, 250 degrees Celsius. And you've been told that it is a perfect emitter, so its emissivity constant is 1, right? You've been told the mass, heat capacity, and volume of your dinner, as well as the time it took to cook it, or the time you expect to have it under the heat lamp to cook it. And the goal is, right, since you're trying to cook things, what you're going to figure out is how much temperature is your dinner or your food down here at the bottom going to increase by uh, in order to, effectively heat something. So you can do this one step at a time. What you're going to want to do first is you're going to want to start at the top, taking a look at this heat lamp, and you're going to want to figure out how much energy it's going to emit in the form of light. This is why there's a little rad down here. It stands for radiation. Now, in order to do this, there's a couple of things that you need to do. The first is, what you'll notice here is this does use the Stefan-Boltzmann constant, and the Stefan-Boltzmann constant is in temperature units of Kelvin. You've been provided with a temperature in degrees Celsius here. So the very first thing you're going to want to do for your heat lamp is you're going to want to convert it to Kelvin. To convert things to Kelvin, what you want to do is you want to take your temperature in Celsius and you want to add 273 to it. And this will give you your temperature in Kelvin that you want, 523 Kelvin. When you're dealing with any type of heat emission type things, make sure you check the units of temperature that are present in the constants that you are given. You need them to match up. Now, with that being said, we can calculate H here. H, what you're going to do is you're going to take the emissivity constant, which is 1. You're then going to multiply it by the Boltzmann constant, 5.67 times 10 to the negative 8, which is in joules seconds per meter squared Kelvin to the 4. And then you're going to multiply that by your temperature in Kelvin, all to the 4. Now, if you multiply this out, what you will get is you'll get 4,247. And as for units left, you will have joules divided by seconds, meters to the squared. Or alternatively, if you want to put it into watts, you'll get a power per unit area, which is 4247 watts per meters squared. And so this is basically telling you how much power per unit area you're delivering to your dinner. Now, with that being said, what you can do with this is you can figure out how much thermal energy you're going to deliver to your dinner over a period of time. Now, this is telling you the rate per unit area you're getting it at. So if you want to figure out the thermal energy that you are delivering to your dinner, right, and this will of course be a change in thermal energy because you have some thermal energy initially. This can be found via the standard heat transfer relationship to change in thermal energy, or the heat Q is equal to mc delta T. Now, this is going to help us find the temperature, but we first of all need to figure out how much thermal energy we're going to get from the system over 10 minutes in a particular area that we're given. To do this, what you're going to want to do is, because you've been provided with a rate here, what you're going to want to do is you're going to take H, you're going to multiply it by the area that you're exposing this thing to, and you're going to multiply it by the time period over which you are heating things up. Now here we have H, which is 4247 joules per second meters squared. We're going to multiply it by the area, which is 0.1 meters squared. And we're going to multiply that by the change in time, or we're going to multiply that by the time over which this is put up. So 10 minutes, we're going to make the units match, and we're going to convert that to 600 seconds. The reason why we're going to convert these 10 minutes to 600 seconds via multiplication by 60 is, at the end of the day, since I want energy, I want the meters squared to cancel out, and I want the seconds to cancel out. Now, if you multiply these all together, you will get your amount of thermal energy. Putting this all together, you'll get 2.54 times 10 to the plus 6 joules. Right, so about 2.5 million joules. Now, with that being said, what we're going to use though is we're going to use this to figure out the change in temperature. So at the bottom here, we have our thermal energy is equal to the mass times the heat capacity times delta T. We have the heat capacity up here, so it's just a matter of putting things together. So given that we know the heat capacity C is 4.184 joules per gram Kelvin, we can first convert it to kilograms because that's how much mass we're going to need to deal with. So you can convert it to kilograms simply by multiplying by 1,000 because there are 1,000 grams in a kilogram. And then we can use that with our energy to find the change in time. So putting this all together, the amount of thermal energy we're going to get over a 10-minute period is 2.54 times 10 to the 6 joules. This is going to be equal to the mass, which is 1 kilogram, times the heat capacity, which we've just put into kilograms as 4.184 joules per kilogram Kelvin. And we're going to use that to find our change in temperature, delta T. I need another bracket here. Right, and again, the unit conversions are done simply so that they match up. We can cross out this kilogram here. We can cross out this kilogram here. Our joules will cancel out, and this will leave us with a change in temperature that's just in Kelvin. If you rearrange this and solve this, what you will get is for your change in temperature, delta T, it'll be about 60 Kelvin. So what this means is if you put your dinner, like say a frozen pizza or something, underneath like this heat lamp, over a 10-minute period, it's going to go up about 60 Kelvin in terms of its temperature. Given that, the heat lamp is 250 degrees Celsius, which is actually hotter than boiling oil. Now, if you've ever cooked something before, if you got something that you're cooking something in that's hotter than boiling oil, and you put the thing there for 10 minutes and it only goes up 60 degrees Celsius, that's not really a whole lot of temperature, all things considered. If you're frying food, you can throw something fried into a pot of boiling oil. It's going to heat up really, really quickly in about a minute as opposed to 10. So what that typically means is when you're heating things up with electromagnetic radiation only, it's not very good. Contact is a much better way of transferring thermal energy than mediating it through light. In fact, the only times that it actually becomes comparable is if you're dealing with something that is ludicrously hot. So the sun is pretty decent at transferring energy via light, but the sun has a temperature that is significantly higher than most of the things that we use on Earth's surface. So basically, if you want to heat something up quickly, instead of just shining a light bulb on it, it's actually faster to take your hot light bulb and then just push it directly into whatever you're dealing with, or mediate it with oil, water, or air, than it is to try to heat something up. And you can see this in your real life, I guess. If you grab a flashlight or an incandescent light bulb and you heat it up, it does get pretty hot. But if you put your hand, a couple of feet away from an incandescent light bulb, your hand doesn't cook as quickly as if you were to touch it. Don't touch the hot light bulb though and burn your hands. But you can calculate this. It's rather useful when you're dealing with photosynthetic type things because you can look at how much heat they're going to gain when they absorb light from the sun.